In our next video here, we're going to talk about work and energy. Power again will come a little bit later. In this case, we're going to talk about the work done by a spring. Now that's, again, kind of a strange concept. It's kind of like work done by gravity. And why is it different from work done by a force on the spring? So here you can see that the force pushes the spring together and compresses the spring. And so therefore, that force does work on the spring. But the spring is pushing back. Newton's third law, for every action, there's an equal and opposite reaction. So the spring is pushing back in the opposite direction. And so you say, well, how can the spring do work if it's pushing back against a force that's pushing it in? So it seems kind of odd, but yes, we should be able to mathematically and using the laws of physics, calculate the work done by the spring. So to make it easier to understand, let's first figure out the work done by the force pushing and compressing the spring together. Of course, the spring has a spring constant K, and we can then say that if we then, of course, incrementally push the spring in by small amounts, because remember, the force required to push in the spring is not a constant, it's equal to K times X. So the more we compress the spring, the more force we need. So it's not a constant force. So we can say that the small amount of work done by moving the spring from this position to a very small position further along, so that this compression distance is only a small dx, we can say that dw is equal to the force at that moment times a small amount of compression. So the work done is going to be equal to force times distance. Now, what is the direction of the force? The direction of the force is, of course, to the left. And the direction of displacement, of course, is to the left. And so we can see that because they're going in the same direction, that we can multiply that times the cosine of the angle between them, which is 0. So here we have the force in the negative direction. That would be minus kx. And of course, I have to make these vector quantities and the dot product, because that's what we are doing here. So we have kx in the x direction, and it's negative because the force is in the negative direction. And then we're going to go ahead and multiply that with a dot product times dx. So dx, and of course, that is also in a negative direction. So maybe I want to put a negative 1 in front of there, minus 1 times dx like that, because my displacement is also from right to left, so that's also negative. So what that means is I have a negative times a negative, which gives me a positive. So this is equal to kx times x hat. So actually, what I should do here is call this a dx times x hat like that. That's probably a more precise way of writing it. So what I have now is I have a minus times a minus, which is a plus, a kx times a dx, and an x hat times x hat. These are the two x unit vectors. They're both 1 unit long, and the angle between them is 0. So it's 1 times the cosine of 0, which is also 1. So this is equal to k times x times dx times 1 times the cosine of 0 degrees, which also, of course, is 1. So that's equal to the work done to move it over a small infinitesimal amount of distance. So now when we integrate both sides, we get the total work done. So work done is equal to the integral of dw, which is equal to k times the integral of x dx, because of course k, the spring constant, is a constant. And the integral of x dx can be written as kx squared over 2. In other words, the work done by the force is equal to 1/2 kx squared. That's kind of a funny looking k, so let me try that again. So this is kx squared. I guess writing down that low makes it a little bit difficult. All right, so now let's try to find the work done by this spring. We use the same exact concept. The dw is equal to the force of the spring dotted with the displacement. Now the force of the spring is still kx, but it's now pointing to the right. So it's a positive kx. So this is equal to a positive kx in the x direction, dotted with the dx, which is dx, and I should write minus dx because the displacement is to the left, which is a negative quantity. So it's a minus dx in the x direction, like so. All right, so now what we have here is we have equal to minus kx dx times the unit vector x times the unit vector x. Of course, there's a dot product The length of unit vectors are 1. The angle between them is 0. The cosine of 0 is 1. So this whole thing simply becomes 1. And this therefore becomes minus kx dx. And that is the work done by a small amount. That's the work done by the spring by displacing the spring just a small amount. So that's actually a dW, not the total work done, but a small amount of work done to compress the spring just a little bit. All right, now we're going to find all of the work. So we're going to integrate. Work is equal to the integral of dW, which is equal to the integral of minus kx dx. Notice that minus k will come out of the integral sign, so this is equal to minus k times the integral of x dx. And then we can go ahead and integrate that, which is an easy integral. It's x squared over 2. So this is equal to minus k x squared over 2. And therefore, we know that the work done is equal to minus 1/2 kx squared, which is, of course, equal in magnitude but opposite in sign to the work done by the force. The spring force is simply a reactionary force, and since the spring can't help contract itself, therefore it's negative work done by the spring. So this is work done by the spring, which therefore has to be negative work, and this is work done by the force compressing the spring together. And that's how you can see how to figure out the work done by the spring.